So in this workshop, we're going to continue exploring the general linear model. Previously, we looked at the general linear model in the context of simple linear regression. What we're going to be doing in this workshop is looking at the model in the context of multiple regression. So simple linear regression is where we had a case of we had one predictor predicting an outcome. In multiple regression, we have more than one predictor predicting an outcome. So, previously in the first workshop on regression, we went from variance to covariance to correlation to simple regression. And in a sense, the purpose of that was really to show that each of these steps in and of themselves is actually a relatively small step, and that regression, which is something that looks fairly complex and is actually really quite useful, is based on some very straightforward ideas. And we discussed how we can think of regression really in terms of prediction. And with the ordinary least squares regression approach that we looked at, we saw that we can build different models as a way of capturing our data, and that we can test how good each of these models is by measuring the extent to which they minimize the residuals. In other words, the difference between the observed data and the linear model that we've built. So multiple regression is an extension of simple linear regression, but rather, as I said, than having just one predictor, we've got several. But ultimately, the goal is broadly the same. We want to end up with an equation for a straight line that is the best fit to our data. In other words, a regression model that minimizes the residuals, the deviation between the model and the actual data points. So in the context of regression where we've got more than one predictor, we can think of it as, we've got a dependent variable or our outcome variable, just say over here. We've got three predictors or three independent variables. They overlap with each other to a little extent, or at least IV2 overlaps with IV3 and IV1, but three of them overlap with the variance in our dependent variable. And we want to know, really, to what extent each of the three individual predictors, each of the three independent variables predicts our outcome. And as you can see in this visualization, there's some variance that's accounted for by both IV1 and IV2. So some variance in our DV is accounted by both IV1 and IV2. And we might want to worry about cases where there's too much of an overlap between the predictors. And that's something we're going to look at. So this is kind of the general idea behind what we're doing in the context of multiple regression. We're looking at sort of multiple predictors. We have to consider a number of things. All throughout the set of workshops, we've been talking about the historical lack of experimental power that has resulted in many journal articles actually overestimating effect sizes, or people thinking they've found effects when the effects aren't actually present. So sample size, again, is something that we need to consider. Do we have enough power to detect the minimal effect size of interest? Do we need to worry about issues related to multicollinearity? So that's where different predictors actually correlate with each other, and also issues related with singularity, where maybe one predictor is arguably a component of another. As with simple linear regression, we need to ensure that our residuals are approximately normal, and that we don't have any issues around skewness, nonlinearity, or homoscedasticity. And again, we also want to think, do we have any outliers or influential cases that might be having an overly influential influence on the sorts of models that we're trying to build? I'm just realized overly influential influence isn't very clear. Basically, do we have any data points that are having too strong an influence on the regression model that we end up with? So, how big a sample size do we need? How big an N do we need? So there are a couple of rules of thumb which you might want to think about using. My preference is always to do data simulation before actually collecting real data to determine whether or not the models I'm wanting to build are able to detect the minimal effect sizes that I might be interested in finding. There's a workshop on data simulation later, but we can use these two rules of thumb initially, where for testing the regression model, our n should be greater than 50 plus 8 times the number of predictors in our model. That's for testing the overall fit of the regression model itself. For testing individual predictors, our n should be greater than or equal to 104 plus the number of predictors. And actually, in most cases, we want to test not just the regression model, we also want to test the individual predictors. So it's always a good idea, going by this rule of thumb approach, to basically calculate both ends and choose the one that produces the largest number. So for example, where we've got 6 predictors in a model, would actually require 98 participants to test the regression equation itself, and 110 participants to test each of the individual predictors, because 104 plus 6 is 110. So we'd actually go with a higher n, which is 110. So for the model that we're wanting to test with 6 predictors, where we want to also test the individual predictors themselves, we'd need a sample size of at least 110, okay? So multicollinearity we need to worry about as well. I've mentioned this briefly. That's when 2 or more variables are highly correlated with each other. We can actually test this by examining what's known as the VIF value for each variable, the variance inflation factor. We also want to worry about singularity, where there's maybe redundancy in one of our variables, because perhaps one of our variables is a combination of two or more of our other independent variables. So say you've got some sort of model or data set where you've got people's height, you've got their weight, but you've also got their body mass index. So we know that body mass index is actually calculated by using the information about the height and weight. So we wouldn't build a model where all 3 of those predictors are in, because the BMI variable would be redundant because it's basically defined by the height and weight variables. So we need to think a little bit in terms of singularity to make sure we don't have any redundancy in any of our variables. And to test for collinearity or multicollinearity, well, we can actually run some diagnostics which will tell us whether or not we have a problem. So as I said, VIF stands for variance inflation factor, and it tells us if the VIF value is too high, whether we need to worry about multicollinearity, correlation between each of our independent variables, between our predictive variables. And we can actually use the car package in R. We can use the VIF function within that package to work out the VIF values for predictors in our models. And as a general rule of thumb, VIF values of greater than 10 suggest that there's a real multicollinearity issue. Although some people say that any values even greater than 5 suggest there's an issue too. And that really you should be conservative when you're building these models. So perhaps it's better to address an issue if you've got VIF values even just greater than 5. So as we looked at in the first workshop on simple regression, we need to ensure that our residuals are normally distributed. So for every predicted score, the observed values around that prediction should be normally distributed. In other words, there should be lots of values, lots of real data points that are quite close to our regression model, and then fewer data points that are kind of further away from our regression models. We'd expect if we plotted our residuals a fairly normal distribution such as this. And we can investigate the distribution of residuals. We could do a plot like this if we wanted to, but more usefully, and again, this is something we looked at when we looked at the performance package in the first regression workshop, is we could look at the data points on a QQ plot where we expect the line and the data points to be roughly diagonal. That would be indicative of the residuals being roughly normal. So, I mean, this kind of goes without saying, but it's worth making explicit that if we're trying to build any sort of linear model, we need to be sure that the relationship that we're wanting to model is actually linear. In other words, can be captured by a straight line. So an increase in the scores of a predictor should be followed by an increase in the scores in the outcome, and vice versa. And there must be a uniform relationship between the fit of values and the error that can be captured by this straight line. A very minor violation of this assumption isn't dire, but it will weaken the power of the analysis to adequately capture the relationship between the two variables. We need to worry a little bit about homoscedasticity, and that's the fact that the standard deviations of errors of prediction should be approximately equal for all predicted scores. In other words, the amount of error is the same roughly at different predicted values of the outcome. And again, violation of this assumption isn't terminal per se, but it does weaken the overall analysis. And we can get around this by not using OLS regression, but perhaps using generalized least squares regression instead. So there are ways to kind of address this issue. Because at the end of the day, your data are your data, and you've got to find the most appropriate model to describe the data as they are. So it's always a really good idea before you do any sort of modeling. I mean, it goes without saying, visualize your data, have a look to see what your data actually look like. I've seen cases in the past of people trying to fit a straight line to data that's actually curvilinear, and you're not going to fit any sensible straight line to sort of data that are actually curved in any shape or form. So visualize your data first. The other assumption is that of outliers. So outliers tend to be data points, cases that don't fit the regression model that well. So they tend to have really large residuals. And outliers can happen for a number of reasons. In, say, reaction time studies, it could simply be because somebody, I don't know, entered their mobile phone or something like that during one particular experimental trial. Maybe they sneezed, maybe they sort of pressed the button too quickly. So you can get outliers that sort of happen for those sorts of reasons. But it can be kind of tricky sometimes to determine what's a real outlier and what actually is just a slightly unusual data point. So there's a bit of a tricky one. And I guess my general rule of thumb in the context of, say, if I was doing analysis of variance, I might think of an outlier as being roughly more than 2.5 standard deviations from the mean, and I might replace an outlier with that point. But it's kind of a judgment call all the time, and hopefully you're not really going to have too many outliers in your real data sets anyway for this to be something that you need to worry about, because you don't want to be removing data points that are actual real data points. So we can spot influential cases using Cook's distance, which actually is one of the diagnostic plots we get out of the performance package, and it'll be indicated when we do the diagnostic plots whether or not an individual data point is perhaps being overly influential. Anyway, so let's go on with natural example. So we're going to look at a case of a linear model where we've got multiple predictors. So totally fictitious data, by the way, so don't try and sort of wonder where I got this from. So we're interested in whether house prices in 250 regions in the UK, whether or not they can be predicted by 4 things. Population size in that region, crime rate in the region, average age of people in the region, average household income of people in the region. Or of households rather, in the region. So this is kind of a fictitious data set. So including our predictor, including our predictors, our outcome, and a column identifying our regions, we'll end up with 6 variables in our data set. So we've got region, house price, that's our outcome variable, population, crime, average age, household income. So the first thing we might want to do is look at the possible correlations between each of the 5 core variables in our data set. So the 5 core variables will be our outcome plus our 4 predictors. So we're actually going to use a package called ggcoreplot, a function rather from the package ggcoreplot, where we're going to build this kind of correlation matrix. So we're going to build a correlation matrix using this syntax here, where we're going to select our data sets. Our data set's actually called my data, and we're excluding region because region is just a factor, and we don't, that's obviously not going to be something that's going to interest us. What we're really interested in is how the 5 variables that we're measuring correlate with each other. So we're going to build this little correlation plot down here. And we can kind of see that there do indeed seem to be some relatively weak correlations between our different variables. So here, house prices seems to be correlated with population. We have a positive correlation between the two. Down here, we've got a negative correlation between crime and house prices. So this would mean that maybe as crime rates go up, house prices go down. So it's quite a handy way to look at some of the relationships. It can also maybe tell us a little bit whether or not we need to worry about correlations between our predictors. So here's average age has a very small positive correlation with household income. Population has got a very small negative correlation with household income. So it's probably not going to be an issue for us. There don't seem to be any obvious strong correlations between our individual predictors if we look at that sort of correlation matrix plot. So we can visualize our data as well. Here I've put on the x-axis on each of these panels house prices, and then I've done 4 plots, one for each of our predictors, and I've fitted a simple regression line just for that one predictor. We can kind of see that for the population variable, as we had in the correlation matrix, we have a weak positive correlation between the 2 variables. For crime, there seems to be a weak negative. So we can kind of have a little bit of a feel just from visualizing the data, what might be going on in our data set. And this kind of helps because when we start building our models, we've already got a bit of an idea as to what those models might reveal. So it's quite handy actually to have a bit of an expectation as to what your models are going to reveal, because if you end up coding your model wrongly and you end up with stuff coming out of your model that doesn't fit what you've seen visualized, you'll not proceed any further. You'll sort out the model. So it's a good idea to do this visualization earlier. So in the same way as we did with simple linear regression, we were building 2 models to begin with. We're going to build 2 models in this case. We're going to build one model with just the intercept as our predictor. So this is kind of, think of this as almost like the null model where we don't have any predictors. We're just using the mean as a predictor. And then we're going to build another model with our 4 predictors: population, crime, average age, and household income. So we've got one model, which is just the mean as a model of our data, and another linear model where we've got each of our 4 predictors in there. So we've got these 2 models, and we're going to compare them to each other using the ANOVA function. So if you remember from last time, this is going to give us an F value, and we get an F value of just greater than 4 and a p-value of 0.00311. We see that the residuals, so the residual sums of squares for our model with our 4 predictors, is actually less than the residuals associated with the mean as a model of our data. We can already see that the model with our 4 predictors has less, the residuals, the error is less, and the F ratio tells us it's a better model than the mean as our model of our data. So we would conclude on the basis of this that our regression equation with our 4 predictors is better as a way of modeling our data than just the mean is. So there's something in our regression model here. We then need to extract the parameter estimates using the summary function. So we're going to say summary and then model 1, and we get the estimates that we need in order to build our regression equation. So again, if you remember back to the first workshop on regression, the intercept here corresponds to the regression line when all other values are set as 0. So it's the intercept. So we've got our 5 parameter estimates here. We've got t-tests associated with each and p-values associated with each t-test. And you kind of might look at this and think, well, hold on, here's something interesting. 2 of our predictors, average age and household income, don't actually look to be significant in and of themselves. So we're just going to park that thought for a minute. We'll come back to it in a little bit. Another bit of the output of the model, we get the R-squared and adjusted R-squared values. So this tells us basically how much variability in our outcome variable is explained by our predictors. As mentioned in the previous workshop, adjusted R-squared values takes on board the number of predictors in our model. So you can see the adjusted R-squared value is quite a little bit lower than the multiple R-squared value over here. But we've got useful information so far. We've got a significant model and we've got information about each of the parameters. Let's just check our assumptions. And I guess on the basis of what we looked at earlier, things looked okay. There's no issue of multicollinearity, so we actually get a visualization here of what the VIF values are between our different predictors, so there's nothing to worry about in this case. Our residuals are nice, they're on the diagonal, so they're normally distributed. You can see again here, the residuals follow the normal distribution quite nicely. We've got data spread roughly equally around this horizontal line, so we've got this assumption met as well. In terms of homogeneity of variance, again, we've got dots spread relatively equally around the horizontal line. Influential cases, well, there's one case out here, but it doesn't look too worrisome, so I'm not going to lose sleep over that. So our assumptions seem pretty nicely met with respect to these sorts of diagnostic tests that we've carried out. So if you noticed back here that neither average age nor household income seem to be significant predictors in and of themselves. So we might think that it would be useful to build a model where we don't have those two predictors in, and we look to see whether or not that model, that simpler model, without those two predictors, is actually better in terms of accounting for our data. Because in a sense, it's kind of very often the trade-off between, we want a model that's good at explaining our data, but we don't want to sort of over-parameterize our model. We don't want to have an overly complex model, because models that are overly parameterized tend to then not be generalizable to other data sets. And you could actually build a linear model that fits your data perfectly, because you could have a coefficient effectively for each data point. So you could have a model that has zero error because it predicts your data set perfectly. But because it's got so many parameters in it, and because it was built just for that one data set, it probably is not going to generalize very well, if at all, to other data sets of the same type. So it's always this kind of trade-off we need to think about in terms of being able to capture the structure of our data, but not end up with a model that's kind of over-parameterized. So we're going to create a new model now. I'm going to call it Model 2, using the linear model function, where we now just have house prices predicted by population and crime numbers. This is a simpler model. And we're going to compare this model with two predictors to our Model 1, which had 4 predictors. Okay? So we can look down here. This is slightly counterintuitive because the labeling actually swaps on the output, so just careful with that. So this first model is our 2 predictors. The second model is our 4 predictors. I will actually see that the F ratio between the two, it suggests there's not a significant difference between our 2 models. The second model with the 4 predictors has got slightly smaller residuals associated with them. But we can also use something else. We can actually use what's known as Akiki information criteria, which is another way of measuring goodness of fit of models. And Akiki information criteria, or AIC, tells us about how much information on our data is not captured by a particular model, with lower values being better. So absolute AIC values by themselves don't tell us anything. You can only interpret AIC values relative to each other. So you can build 2 or 3 different models, or actually many different models, on the same data set, calculate the AIC value for each model, and then if you wanted to, if you're doing it on the basis of AIC selection, you'd actually select the model which has got the lowest AIC value. So let's look at the AIC values for our 2 models. So Model 1, that's the one with the 4 predictors, has got 5290. Model 2, the AIC value is 5286. And we can actually see that Model 2 has actually got the lower AIC value. And that's because AIC actually penalizes models with increasing numbers of parameters. So as you add parameters into your model, you can think of it as then being that like that extra parameter has to kind of justify its existence. So if you add a parameter after parameter after parameter, your penalty will increase if as a function of what those parameters then need to do. Related to AIC is BIC, Bayesian Information Criteria, which also penalizes parameters when you add them, but even more so than AIC. So we might go for the AIC section in this case, in which case we will go for Model 2. So that's the model where we're predicting house prices with just 2 predictors. So if we're going for that, let's check our assumptions again. Doesn't look as if there are any collinearity issues. If there were, one of these would be highlighted. Nothing's highlighted here. Residuals look fine, both of these plots. Homoscedasticity looks fine. Homogeneity variance looks fine. And again, nothing overly concerning here in terms of Cook's distance. So we might, basically select Model 2 on the basis of this. Now, one other assumption we need to think about is that of non-independence of errors. In other words, our errors need to be independent of each other. This is just one of the other assumptions of regression. And we can test that explicitly using the Durbin-Watson test approach, which is a function in the car package. So if we actually, apply our model with the 2 parameters to the Durbin-Watson test, we get a number of statistics reported. We get the Durbin-Watson statistic itself and also a p-value. And basically, a value of around 2 means that there's no autocorrelation in our sample, which basically means that we can conclude our errors are independent of each other. So we've met that other assumption of regression in this case. So you can imagine for linear models, regression models where I've got lots and lots of different predictors, a very rich data set, it could be a bit cumbersome to be manually building different models and sort of comparing and contrasting and whatnot. So there are sort of automated ways in which we can arrive at the best model using a number of different sort of rules for what defines a best model. So we're going to look at stepwise regression based on AIC improvements. So basically this will give us a model, a regression model that has got the lowest AIC value. So we can use this. We're going to give it a starting model and then kind of the most complex model, and it's going to work between these 2 limits to arrive at the model with the lowest AIC value in terms of the number of predictors. So it kind of works within the scope of the null model where we've just got the mean as our model of our data, and the full model where we've maybe got all of our predictors in there, and actually finds the model between those 2 limits that actually gives us the lower or the lowest AIC value. So we can use the step function to do that. We can map it onto a variable I'm calling the stat limits both, because we're kind of working from both ends to kind of hone in on that sort of optimal model, somewhere between the 2 limits that we've defined. And we can ask for a summary of the model that it ends up with, and by using this automated procedure, it says that the best model for us in terms of the model with the lowest AIC value is the one where we've got house prices predicted by crime and population, which is exactly the same model that we arrived at manually. And we get the model parameter estimates here, the individual t values here, and you see that the AIC value that of the best model it arrived at is the same as the AIC value of the one that we sort of built ourselves manually. So stepwise regression based on AIC improvement is pretty handy for doing that. We can also work out, in addition to parameter estimates themselves, we can also work out the confidence intervals of the parameter estimates. So we can estimate the confidence intervals for each of these parameter estimates in our model using the confint function. And And what this basically means is that if we were to repeat the study, hundreds or thousands of times, and about 95% of calculated confidence intervals will include the true value of the parameter, because remember, our data set that we have is just, one possible data set from a whole, bit sampled from a population. And as we do take a different sample from the population, things will change very slightly in terms of what our sample is. But we can actually then use the confidence intervals function as a way of estimating the confidence intervals associated with those coefficient estimates, such that 95% of the calculated confidence intervals will actually include the true value of the parameter as it is in the population. So in addition to regression models based on AIC, improvement to AIC, minimizing AIC, we can also build models on the basis of improving our R-squared values. Kind of think of this as like, again, sort of an explanatory power type of measure of sort of goodness of our models. And we can use the OLS step forward function from the OLS RR package to actually do that, where we'll start with a model and it will basically, again, iterate through and work out the best model on the basis of, say, p-value and adjusted R-squared improvement. So I'm using the OLS step forward p function, so we're going to do it based on improving the p-value. I'm going to map it onto my variable called p-model, and we can kind of look at the output here, and it's pretty much the same thing, isn't it? We've got our model where we've got our house prices predicted by crime and population. Okay, so we've got the same sort of model arrived at here, but in a different in a different way. And what's quite nice about this approach or this example is that both the p-value improvement approach and the AIC value approach have actually generated, they settled on the same best model for us to have. But this may not always be the case, so you need to think about which one you're going to use. And if you're going to go down the pre-registration route for your research, it's always a good idea to specify as much as you can in your pre-registration. So if you're going to do your model selection based on, say, AIC value minimization, make that explicit in your analysis plan. So we're going to use, the check model function in the performance package to look at the model diagnostics. We can use VIF function as well in the car package to look to say whether or not we've got any collinearity issue, and we don't. Basically, the VIF values for both of our predictors are around about 1. So we don't have a collinearity problem in this case, as I mentioned previously. Values greater than 10 or even 5 would have suggested a multicollinearity problem, so we're well away from that. We can ask for the outputs, the output of our model, and again, it's just the same as what we had earlier. We get the intercept, and then we get the coefficients associated with our two predictors, okay? So we want to ultimately write a regression equation using these parameter estimates here, because we want to be able to predict house prices on the basis of other things. So we can take these values here. So this notation here means that we need to move the decimal place 5 points to the right. You've got plus here, so it means 5 points to the right. Down here, because the sign is a minus, it's -1, we have to move the decimal point 1 place to the left. So our regression equation is such that a house price in a region is equal to 173,600, which is this coefficient here, minus 334.3 multiplied by our crime variable, plus 0.6662 multiplied by our population variable, plus some sort of residual. So this regression equation is a way of capturing the relationship and the nature of the relationship between our predictors in this case crime and population, and our outcome variable, which is house prices. So we can conclude on the basis of this regression equation that crime has a negative influence on house prices, because as our crime value goes up, this number will get bigger, so more will be knocked off our house price. While population size has a positive influence on house prices, because as population goes up, this number here, because population multiplied by this number here, as population goes up, then this product will go up, and house prices will go up. So we've got a fairly nice regression equation with a fairly clear story that house prices are negatively related to crime. As crime increases, house prices go down. But house prices are positively related to population size. As population size increases, house prices go up. So that's what we would conclude on the basis of the model that we built, and this is the regression equation that we would write to capture the nature of the relationships between the variables in our data set. So just moving on towards the end now, I want to talk about a couple of things briefly. I want to introduce you to the concept of mediation. So sometimes a variable's power of prediction of an outcome is lost or reduced when another predictor is introduced. So this extra variable actually mediates the initial effect by its absence and cancels the effect by its presence. So here's an example down here where I've got an influence of x on y, but actually when we add our mediator, the direct effect of x and y is no longer significant. X affects our mediator, so this is a positive relationship here, and our mediator affects significantly our outcome variable. So rather than the direct relationship between x and y now being significant, it actually goes through this mediator up here. So if you've come across mediation in another course you might have done, you may not have, by the way, but sometimes it's covered in undergraduate levels. You may have encountered the Sobel test for using mediation. It's very conservative, or can be very conservative. And nowadays, people tend to use bootstrapping for understanding mediation. And within the context of R, there's a package called mediation, which is kind of the go-to package for doing these sorts of analyses. So I want to take a brief diversion at this point just to talk a little bit about bootstrapping. So bootstrapping can be quite useful for small samples. So imagine you've got a sample of, say, n measurements. You can sample these measurements in many ways, as long as you allow some values to appear more than once and others to be left out. So you're kind of like sampling and resampling from your data set. And what you could do when you take a small sample from your data set multiple times, each time you can calculate the mean. You could do this like 10,000 times. If you've got a data set of 100 data points, you could work out sample sizes of 50 from that data set. And each time you extract a sample size, you work out the mean. You could do this, say, 10,000 times. And then you can actually start to understand properties of the population that you're sampling from. And this is really the basis of bootstrapping. So imagine we've got, we measure the speed of 25 military planes, and we're plotting the data in a histogram. Well, we might think to ourselves, well, what might the underlying population planes look like that we're sampling from, given we only know really about this one sample? So we can actually use bootstrapping to start to investigate that and give us some sort of estimates as to what the population might look like that we're actually sampling from. So here's a little example where I'm doing 10,000 samples based on our 25 observations. So what I'm basically doing is sampling from our data set 10,000 times. And then I'm working out the averages for each of these samples, and then I'm plotting those in a histogram. And this gives us an approximation of the population that we're sampling from. And we can use this population to estimate parameters such as the likely mean of the population, but also confidence intervals as well. So by doing this bootstrapping, if we measure a plane, say with speed of less than 950 miles an hour or whatever, How likely is that given our estimated population? Well, we can actually work out where in this bootstrapped population that point actually lies. So we can work out how many planes have a speed of, say, 950 or less, and it works out to be around 18 or so in our sample of 10,000. So basically it gives us a probability of less than or equal to 0.0018 that if we were to sample a plane, we'd get one that has a speed of less than 950. So bootstrapping can be quite useful in terms of helping you maybe understand a little bit about the population that you're sampling from. So bootstrapping is kind of used in the mediation package as a way of kind of estimating the parameter values. So let's look at an example. So imagine I should say this is from a great web tutorial I found by Alexander Demos and Carlos Salas, which I thoroughly recommend you check out. And it's a nice example. So the case is that we're interested in whether or not the number of hours since dawn affects the subjective ratings of wakefulness of 100 graduate students through the consumption on coffee. Okay, so coffee is our mediator, and we want to know what the influence of number of hours since dawn affects, feelings of wakefulness as mediated by coffee consumption. So we're going to use the mediation package in R, which is based on the Preacher and Hayes method from 2004. We're going to build two models. One model, so we're going to use the linear model function again. We're going to build one model where we have a direct effect of our predictor, and another model where we've got an effect of our predictor and of our mediator. Okay, so our first model, we've got an effect of our predictor on the mediator, and then the second model, we've got effect of our predictor and our mediator on our outcome. Okay, so we've built these two models, and we're going to compare the two models to each other using the mediate function in the mediation package, which will allow us then to estimate the effect of our mediator. So we're going to map it onto a variable I'm just calling fitmed. So we're going to use the mediate function with the two models that we've built. Our treatment or predictor is represented by our x variable, and our mediator is m. So by looking at the summary of the output of the mediate function, we get a number of important bits of information. We get the average causal mediation effects. We get the estimate for that there. We get the average direct effects, and then we have the combined indirect and direct effects, and then the ratio of the estimates here. So the average causal mediation effect is the indirect effect of m, and the associated p-value tells us if our mediation effect, or if our mediator is significant. And we can bootstrap our data and fit a model based on our estimated population parameters, which is actually recommended over using this confidence interval estimation method up here. So we're going to do that using bootstrapping. So we just add this extra parameter. We're asking for 10,000 bootstrap simulations in the mediate function. I get the same sort of information reported here. We get the average causal mediation effect here. It's still significant. But if you look now, the total effect, which was significant here, now isn't significant. So we would interpret this output as meaning that all we've got is a significant effect of our mediator with no direct effect of our predictor or combined effect of predictor and mediator when the mediator is taken into consideration. So it's you may come across mediation in some of your research. This is kind of how you would go about doing it. I'm not going to go into any more detail about it. It's really to kind of just introduce you to to the concept and go through a little worked example. But as I say, check out that great book by Alexander and Carlos. It's really worth looking at. Okay, so we're now going to move on to moderation. People very often get mediation and moderation mixed up. I'm not quite sure why. They both begin with M, but that's about it, really. So moderation is, you can think of it in terms of the kinds of interaction effects you get in factorial ANOVA, where the strength of the relationship between two variables might actually change as a function of some third variable. So think of this as kind of a moderation is kind of the interaction effects that you might find. So let's look at the specific example where we're interested in whether the relationship between the number of hours of sleep that a student receives and the attention they pay to this lecture is influenced by their coffee consumption. So we've got these three variables. We've got an outcome variable, which is attention that they pay, and a predictor variable, hours of sleep, and a possible moderator, which is coffee consumption. So it could be the case that coffee consumption interacts with hours of sleep to ultimately determine the amount of attention students pay. So as with any regression or linear model that we're building, it's always a good idea if you have continuous predictors to center them. You might want to scale them too, although in this case I'm just centering them, as it makes interpretation of the parameter estimates often a lot easier. So what I'm doing here is creating two new variables. One's called xc, and that's basically simply our x variable scaled and centered, or centered rather. I'm not scaling it. I'm doing the same thing for our coffee consumption variable, creating a new variable called zc, which is basically the coffee predictor centered. Okay, so we're centering our two predictors. So now we're going to build our model where we've got y, which is attention paid, is predicted by hours of sleep plus coffee consumption plus these two things interacting with each other. That's what the little colon indicates there. So we can see that when we build this model, we get our parameter estimates as usual. We have a significant predictor of hours of sleep. We've got a significant predictor associated with coffee consumption, but importantly, these two predictors interact with each other. Okay, so we have an effect of moderation, or we have an interaction effect between hours of sleep and coffee consumption. So what does this mean? Okay, so it's easiest to interpret with a bit of a visualization. And we're going to do that using the plot slopes function in the RockChalk package. And we're going to plot the slopes of our moderating effect, one standard deviation above and one standard deviation below the mean. Okay, so if we look at this plot down here, we've got three lines drawn. We've got a solid black line, a dotted blue line, and then a dotted green line. So what that plot indicates is that the black solid line, which is those who drank less coffee, because you see up here the black solid line corresponds to the mean of that variable minus standard deviation. So those who drank less coffee, the black solid line, paid more attention with the more sleep that they got last night. That's actually true for all three, but but they actually paid less attention overall than average, which is indicated by this blue dotted line. So although each of these three lines each goes up, in other words, attention paid increases as a function of number of hours sleep the night before. So remember, we actually centered this variable, so this isn't 0 hours, this is actually the sleep variable centered. So although for everybody, the more sleep you get the night before, the more attention you pay, what we actually find is that this interacts with the amount of coffee you drink as well. So those people who drink less coffee than average, which is the solid black line, paid less attention overall than those who drank an average amount of coffee. Those who drank more coffee overall, as indicated by the dotted green line, paid more attention when they slept more, as well as paying more attention on average. So the amount of attention you pay in your lectures is predicted not just by sleep and coffee consumption, but the two actually interact with each other. And the difference in the slopes for those who drank more or less coffee shows that coffee consumption actually moderates the relationship between hours of sleep and attention paid in the lecture. So that's really all I want to say about moderation in this context. So we've done quite a lot. We've gone from, in the previous workshop, looking at simple linear regression, which is based on variance and covariance and Pearson's R. In this workshop, we've then looked at multiple regression, where we've got multiple predictors. We've looked at the different ways in which you can build up models, multiple regression models with multiple predictors, different ways in which you might select the kind of the best model, whether it's on the basis of p-value improvement or minimizing your AIC value. Very often these will result in the same sort of thing, but not always. So we looked at different ways of determining our best model. We then looked at the various diagnostics that we carry out to ensure that we've met the assumptions of parametric tests. Many of these diagnostics can be sort of visualized using the performance package. We also looked at the Durbin-Watson test as well, of ensuring that our errors were independent of each other. And then we went on to kind of understand how we interpret the output of a regression model and how we take those coefficients from a regression model output and ultimately build a regression equation which will allow us to predict some outcome variable if we know the values of some predictor variables and how to interpret that. Before then moving on to the case of mediation, where the relationship between two variables might actually change or disappear as a function of a mediator being added. And then finally we looked at the case of moderation, which is really to do with focusing on interaction effects in the context of regression, where the magnitude of the relationship or magnitude of the strength of the relationship rather between two variables changes as a function of the value of some additional variable. So covered quite a lot. Hopefully it's all kind of built incrementally on top of each other. Each bit's built incrementally on top of each other. So what I would like you to do now is take a wee break, obviously, and then work through the worksheet where you'll be building different sorts of regression models, looking at different ways to build the best regression model, and checking out some of these sort of model diagnostics yourselves.